Good morning, afternoon, or evening. How y'all doing today? Welcome back to Mr. Moore's Honors Geometry class. Today we're going to be talking about a very cool and fun and very useful theorem called the Pythagorean Theorem. Now, the Pythagorean Theorem is very useful not only in geometry, but also in trigonometry, Algebra 1, Algebra 2, and beyond. It's useful and will be seen in the SAT and the ACT as well, many standardized tests. The Pythagorean theorem is really cool and really powerful, and sometimes it's known as geometry's most elegant theorem. Now, before we get into the meat and potatoes of this awesome theorem and start working some examples and learn it, I wanted to give you just a brief little historical background to this. Now, since it is called the Pythagorean theorem, a lot of people think that Pythagoras, who was a Greek mathematician, invented it. Well, that's actually technically wrong. Pythagoras did not invent this theorem. He actually got it from the Babylonians. The Babylonians created this theorem, and they had this tablet written in Babylonian cuneiform. And Pythagoras deciphered this tablet, translated it to Greek, and actually made applications for it. So Pythagoras really innovated or brought to life the Pythagorean theorem, but the Babylonians were actually the ones who invented it. So I figured you would enjoy that tidbit of history. So now that's done, let's get to it. For any right triangle, okay, c squared equals a squared plus b squared. All right, that's fantastic. What is this a, b, and c? Well, the legs of the right triangle could be leg A and or B. It doesn't matter which leg you call A or B. You could call this over here the vertical leg A and the horizontal leg B, or like I had it before, you could call the vertical leg B and the horizontal leg A. So the A and the B really doesn't matter. What does matter, what is of absolute importance, what never changes, is the C. And the C is the hypotenuse. How do you know that the C is the hypotenuse? Well, there's going to be two things here that determine the hypotenuse. The hypotenuse, which is known as C in the Pythagorean theorem, always is the largest side of the triangle, okay? It will always be the largest side of the triangle. So a very popular, what's called Pythagorean triple. These are right triangles that have already been defined as right triangles. These are set in stone. They're called Pythagorean triples. And the most basic one is a 3, 4, 5 triangle. 5 being the largest side, 5 being the hypotenuse. So the hypotenuse will always be the largest side of a right triangle, no matter what. If it's a right triangle, the hypotenuse will always be the largest side. And another cool thing is that the hypotenuse is always directly across from the right angle, and vice versa. The right angle is always across from the hypotenuse. So if you see where the right angle is, the hypotenuse is the side directly across from the right angle. Now the cool thing about, well, one of the many cool things about the Pythagorean theorem is that it doesn't always have to equal a squared plus b squared, okay? If c squared equals a squared plus b squared, then you will always have a right triangle, period. There's no discussion here, that's just the way it goes. If c squared equals a squared plus b squared, you got a right triangle. However, if c squared is less than a squared plus b squared, you have what's called an acute triangle. And lastly, if c squared is greater than a squared plus b squared, you're going to have an obtuse triangle. Now you already know, Hopefully you remember what these triangles are. Remember, right triangle? It's a triangle with one 90-degree angle. It's pretty self-explanatory. An acute triangle is a triangle where all of the angles are less than 90 degrees. And an obtuse triangle is a triangle where you have one angle that is greater than 90 but less than 180 degrees. So this is the Pythagorean theorem, my friends. This is it. Really cool stuff. Now, we're going to be working with the Pythagorean theorems. And later on in the chapter, we're going to have a whole section dedicated to what's called the Pythagorean triples. However, it will behoove you to start memorizing the Pythagorean triples now. So let's just take a quick look at the Pythagorean triples. Okay? Took you to this website here. And the Pythagorean triples, it talks to you about, first of all, what the Pythagorean theorem is. We know that it's already c squared equals a squared plus b squared. It talks to you about the formation of the right triangle, why it is the way it is. And then what's really cool is here at the bottom, it gives you some basic Pythagorean triples. Now, I'm a realistic person, okay? And I understand that you're not going to memorize every single Pythagorean triple. In fact, it's impossible. I mean, not impossible, but very, very, very unlikely because there are an infinite number of Pythagorean triples, okay? I do want you to memorize the following, though. I want you to memorize the 3, 4, 5, the 5, 12, 13, the 7, 24, 25, the 8, 15, 17, the 9, 40, 41, and that's about it for right now. Okay? If you want to learn more of them, that's great. That's awesome. I'm very proud of you. But those 5 are pretty much the basic that you're going to see in a lot of math application. And those are the basic ones that you're going to see on SATs and ACTs. So if you know these, it's going to save you the time of actually making calculations to find one of the third missing sides. Now, a little hint, and we'll get more into detail with this. Not only are these 5 that I want you to memorize Pythagorean triples, but any multiples of those exact sets of numbers are also Pythagorean triples. So for example, a 3, 4, 5 is a Pythagorean triple, but if I multiply each of those by 2, then that means a 6, 8, 10 is also a Pythagorean triple based on the 3, 4, 5. And any multiple of the 3, 4, 5 will also be a Pythagorean triple. So if I have a 30, 40, 50, that is also a Pythagorean triple. Okay? So like I said, we're going to get more into depth into the Pythagorean triples and how to apply it and how to use it, but it will definitely behoove you for you to learn these 5 Pythagorean triples as of now. So thank you for doing that for me and for yourself. Okay, so let's get back to the lesson. Let's apply this Pythagorean triple stuff. First off, solve for x. So you have a 6, 8, and a blank. Okay, well, 6 is my A, or B, it doesn't matter. 8 is my B. So x is my C. Okay, I like to label, I like to see what's going on. So C squared equals A squared plus B squared. So x squared, which is my C in this case, equals 36 plus 64. So x squared equals 100. Please remember that you get rid of a power of 2 by taking the square root of both sides. And x equals technically plus or minus 100. But since we're dealing with geometry, we're dealing with figures, we're dealing with length, this negative will never be a part of the solution for a distance. So we can go ahead and always, when we're using the Pythagorean theorem, just use the positive answer or the positive root of a square root. So my answer would be, and I messed up here, it's not 100, it's 10. The square root of 100 is 10. So x will equal 10. Now, I know you just saw them, and I don't expect you to see it, but I'm sure some of you have seen the fact that this 6, 8, 10 is a derivation of a 3, 4, 5 triangle. If you can see, my friends, that 6 and 8 come from 3 times 2 and 4 times 2, then automatically you know this is a 3, 4, 5 triangle times 2. So without even using the formula, you could have said x was 10 if you knew the Pythagorean triples. That's the power of the triples. Okay, next. Example 2, find the perimeter of the rectangle shown. Okay, so you have this rectangle. Please remember, my friends, that rectangles have 90 degrees at all corners. So in this particular case, and yes, I'll go ahead and say it right now. I'm sure some of you are looking at this and saying, wait a second. Isn't this a 5, 12, 13? Yes, it is. If you know your Pythagorean triples, you can automatically say that x is 12. But let's say that you don't see that, or that you don't recognize it as of yet, or you don't know your Pythagorean triples. Let's go ahead and label and solve for x the long way, properly. So let's go ahead and say that x equals a. Let's say that 5 is your b. Those are the legs. It really doesn't matter who you designate as a or b, but for sure C 13 is c. So I have c squared equals a squared plus b squared. Okay, 13 squared is 169, which equals x squared plus 25, which is 5 squared. Subtract 25 to both sides. You're going to get 144 equals x squared. The square root of 144 is 12, so x equals 12. And yes, technically it's plus or minus 12, but since we're dealing with an actual length of figure, it's only positive 12. Okay? So knowing the Pythagorean triple makes this infinitely easier, but even if you don't know it or don't see it or don't recognize it, you can always use the Pythagorean theorem. Example 3. Here I have, find the perimeter of the rhombus with diagonals of 6 and 10. Okay? Well, let's think about this here. Why do I have this 3 and this 5 here if they're telling me that the diagonal is 6 and 10? Well, please remember, my friends, that the diagonals of a rhombus are perpendicular bisectors of each other. So I just put 1/2 of it. It's really 3, and this other half is 3. This longer diagonal, I have 1/2 is 5, but the other half is 5. And please remember again that it is perpendicular bisector, so this is a 90. Now, for some of you, you're going to say, wait, this is a 3, 4, 5 triangle. No, it is not. In this particular case, the 3 is a side and the 5 is a side. You cannot make this x a 4 because it is across the 90. And remember what we said, the hypotenuse is always the largest side of a triangle. So this is not a 3, 4, 5 triangle. So please be careful with that. But we can very easily find my x, okay, the side of the rhombus, by using the Pythagorean theorem. X is your C. Let's go ahead and call 3 your A and 5 your B. So I have C squared, which is x squared, equals A squared, which is 3 squared, plus B squared, which is 5 squared. So I have x squared equals 9 plus 25. So x squared equals this 34. I want to solve for x, so I take the square root of both sides, and therefore x equals the square root of 34. Okay? And again, it is technically plus or minus square root of 34, but we do not use the negative roots when we're talking about real figures and distances and lengths. So x is the square root of 34. Okay, that's awesome. So this is square root of 34. But I want to find the perimeter of this rhombus. Please remember that a rhombus is a quadrilateral with 4 congruent sides where the diagonals are perpendicular bisectors of each other. So therefore, this side is square root of 34, this side is square root of 34, and this side is square root of 34, making the perimeter 4 times the square root of 34. Because if you add up the square root of 34 4 times, you're going to get 4 square root of 34. Okay? Hopefully you're seeing this is kind of cool, kind of neat, and fun. Okay, example 4. Nadia skipped 3 meters north, then 2 meters east, then 4 meters north, then 13 meters east, and 1 meter north. Okay, I put this grid up here just to show you the never eat soggy waffles. Okay, north, east, south, and west. I always remember it by saying that phrase, never eat soggy waffles. Okay, never eat soggy waffles. So that's a nice way to remember north, east, south, and west. Now I'm going to disregard the actual units of this grid, and I'm going to write my own distances here, but I'm just going to use the grid just so we can use the north, east, south, and west as a nice little reference. Let's just say that Nadia's starting over here, okay? And she skips 3 meters north, so she goes up 3 meters. And then she heads east 2 meters. So that's 2 meters east. Then she heads north 4 meters. And then she heads east 13 meters. And then she heads north 1 meter. Again, my distances here are totally inaccurate. They're not based on the grid. I just used generic distances here just to portray what's going on here. I want to know how far is Nadia from where she started. Okay, how far is Nadia from where she started? So basically, I'm looking for what is the distance from here, from where she started, to here, where she ended. So I'm looking for this distance right here. Now, we could use, I guess, the distance formula, but then we got to figure out exactly where she started. We have to use exact increments and find the ordered pairs. But we could do that. But a better way, a cooler way in my opinion, is to create a right triangle here. Okay, let's look at how far she went north in total. Didn't she go up 3, then up 4, then up 1? So didn't she really go up a total of 8 meters? And how far did she go to the east? Well, didn't she travel 2, then 13? So didn't she really travel east 15 meters? Well, guess what? If we have a vertical, which is here in blue, albeit not a very straight line, but it is a vertical distance, and we have an intersecting horizontal distance, hopefully remember that when a horizontal and a vertical line intersect, that creates a right triangle, or a right angle rather. And remember, what side is across every single right angle in a right triangle? The hypotenuse. So that is my C. 8 can be my A, and 15 can be my B. So let's solve the distance from where she started to where she ended, which is side C, by using the Pythagorean Theorem. So C squared equals A squared plus B squared. So I have C squared equals 64 plus 15 squared, which is 225. C squared equals 289. I solve for C by taking the square root of both sides. to cancel out the power of 2, the exponent of 2, and c equals plus or minus 17 in reality, but we disregard the negative 17 because we are talking about a distance. So she actually traveled from start to finish. If she made that straight line distance, she went 17 meters if she took that diagonal route. Okay, that's how far she is from where she started. Because remember, back when we talked about points and lines, the shortest distance from any 2 points is a straight line. So if I wanted to find out how far is she from where she started to where she ended, I would want to find this straight line. Okay? Pretty cool. All right, so let us continue. Number 5, find the altitude of an isosceles trapezoid whose sides have lengths of 10, 30, 10, and 20. Okay, well, let's think about this here for a second. There's 4 values here, 4 sides. We know that if it's an isosceles trapezoid, these 2 legs are congruent. Please remember that. Okay, and also these base angles are congruent, and these top base angles are congruent. Okay, just remember your quadrilateral facts. So, since the 2 legs are congruent, we know that this 10 and this 10 are designated to these 2 legs right here. And then just by looking at this figure, the 20 has to be the top base because it's shorter, and the 30 would have to be the bottom base because it's shorter once again. Okay? So, what happens here now? Well, let's think about this. I want to find the altitude. The altitude is this straight line, right, that forms a 90-degree angle, correct? That's what an altitude is. Well, if I want to find that altitude, I'm going to have to use some logic. If I go ahead and make an altitude from this vertex here and another altitude from this vertex here, okay, from here to here is 20. So that means that from this base to this base is 20. So that means that I have these 2 lengths have to be 10 in total. Since we're talking about isosceles trapezoids here, we know they're going to be split down the middle. So this is going to be 5, and this will also be 5. Okay? And I want to find the height. So in this particular case, I can call x A, I can call 5b, and 10 is my c because it is opposite the right angle. So that is my hypotenuse. So let's go ahead and plug it in. We've got c squared, which is 10 squared, equals a squared, which is x squared, plus b squared, which is 5 squared. So I've got 10 squared, which is 100, equals x squared, plus 5 squared, which is 25. Subtract 25 to both sides. And now I have 75 equals x squared. I go ahead and square root both sides. So x equals the square root of 75. Remember that we've already reviewed how to simplify radicals. 75, think of perfect squares. This is 25 times 3. The square root of 25 is 5 with a radical 3 left over. And that is the altitude x of this trapezoid. Okay? Hopefully you see how cool that is. And last but not least, I give you this triangle here and I say classify the triangles shown. Well, it's either going to be a right triangle if c squared equals a squared plus b squared, or a acute triangle if c squared is less than a squared plus b squared, or an obtuse triangle if c squared is greater than a squared plus b squared. Now, the question you may have here is, okay, Mr. Morrow, that's all fine and good, but how do you know which you're going to label as C here? Since we don't have a right angle, we can't, say, oh, it's the side opposite the right angle. Always remember that your C is always going to be the largest side of the right triangle. So we're going to assume always that it's a right triangle, and we're going to use the largest side as C. So 8 will be my C, and then I can call this A and this B. And let's see what kind of a triangle we have. So we've got 8 squared equals 7 squared plus 5 squared. So 64 equals 49 plus 25. 64 equals 74. Wait a second. It does not equal. 64 is actually less than 74. So since c squared is less than a squared plus b squared, this is an acute triangle. And that's the power and the awesomeness of the Pythagorean theorem. Hope you learned a lot. Thank you very much, and have a wonderful day. Bye-bye.